everyone at our 5th press conference of the day. Geothermal energy versus carbon dioxide storage. Can we use the underground more than once? Well, we have invited 4 experts to talk about these matters. First of all, there's Frank Schilling on the right. He is professor in petrophysics of the Institute of Applied Geosciences of the Karlsruhe Institute of Technology. Then we have on his left Jan Diederik van Wees. He's principal scientist on geothermal energy from the Dutch Research Institute, TNO. We have Michael Koen, the EGU division leader of Energy, Resources and Environment. And finally, Herman Held, who will also start the presentation. He is the chair of Sustainability and Global Change of the University of Hamburg and also works at the Potsdam Institute for Climate Impact Research. So Herman, please go ahead.
Yeah, thanks a lot. The 2-degree target was embraced at the last conference of the parties in Cancun, as you know. And here we would like to ask the question, what are the consequences of such a target if it were taken seriously for the energy mix, and in particular for 2 mitigation technologies where our division is particularly strong at. This is carbon capture and storage and also geothermal energy use. So in fact I'm with the still guest at the Potsdam Institute, and most of the findings that I will talk about have been accumulated there. So the costs of transforming the energy system, this is one of the major questions that society asked. What will it cost if we go for a strict mitigation target? And this question has been asked for many decades, but there is now some convergence among climate economics that in fact the costs are rather modest. So there is no, I would say, no perfect agreement yet, but the group of economists that says in principle an economy can deal with this and the costs are rather low is growing. So the costs are estimated of being 0.5% to 2% of GDP on average accumulated over this whole century. So these are the costs of the 2-degree target, the cost of switching the energy system. And this is possible because the economists assume a rather broad technology portfolio. They're assuming the use of various renewable energy sources, the increase of energy efficiency, the use of carbon capture and storage, which we call CCS in the following, and some of them also consider nuclear fission. Here, the ordering has some meaning. The most important I mentioned before at the first, and nuclear turns out to be the least important option. Now, we would like to focus in the following on some of these technologies, and we find that for CCS, in fact, the additional economic value, if you allow for CCS, is rather modest if you go for a modest interpretation of the 2-degree target. You may ask, what is an interpretation of the 2-degree target? It sounds so clear. But the link from emissions to temperature rise is not so clear. There's some uncertainty coming with it, and if you talk about a temperature target, you need to specify at the same time at which probability you would like to observe the target. And a modest interpretation of the 2-degree target could be called a 50-50 chance. Yeah? That the probability of observing it having a certain line of emission cuts is 50% and not more. So this is one of the interpretations that is very often given to the 2-degree target. And in this case, if you go for this interpretation, the additional economic value of CCS is rather modest. The more technologies you have available, the more flexible the energy and the economic system is, and the more costs you save. And therefore, if you are not allowing for technology, it becomes more expensive. Another finding is, nevertheless, if you go for a stricter interpretation of the 2-degree target, for higher probability, something beyond 75%, or you could also rephrase it. If you ask for a stricter temperature target, for example, in order to save the Greenland ice sheet with a high probability, most researchers would assume that at a temperature rise of 2 degrees, Greenland ice sheet would be lost in the long run. So they claim you need a 1 to 1.5 degree target. And in this case, we find that CCS is indispensable. You cannot comply with such a stricter target without CCS, given the present-day portfolio of energy technologies. If there's a fancy technology X in the future, things may change, but if you talk about the portfolio that is at hand at the moment, CCS is indispensable in such a scenario where you go for a very strict mitigation target. Or if you significantly delay mitigation, then we need more aggressive mitigation in the future in order to still comply with the 2 degree target, then also CCS becomes indispensable. And finally, we would like to point out that all this talk about the costs is from a very made from a very aggregate level, a very aggregate economic level, is not really taking the point of view of a company. And there is some suspicion that companies may underinvest in certain mitigation technologies and may not do an as proper job as they could do in terms of security of the technologies. And here we suggest some economic tools to maximize the incentive for a company that would undertake CCS to choose the safest geological formations. So this I will explain a little bit more. But first of all, to the third point. So there is a so-called budget approach, and the underlying this budget approach is the finding that there is a very simple, approximately a very simple relation between the 2 degree target on the one hand and the total amount of CO2 that humankind is still allowed to emit on the other hand. This means if we start cutting down emissions, global emissions right now, we can have a very smooth curve given here in green, whereas if we wait with emission cuts until 2020, our emission cuts must be much more stringent. And we may even overshoot any possibility to comply with the 2 degree target if we wait further. Yeah? The business as usual path would mean an increase, an unlimited increase of CO2 emissions until the end of the century, until to 3 times to 5 times unfolding of the global emissions. So this means if we overshoot this budget, we need negative emissions in the second half of the century. We need a net drawdown of CO2 in the second half if we overshoot in the first half, overshoot the total budget. And this could be performed, in fact, by the means of CCS. If you use biomass, the plants would draw down CO2 from the atmosphere, produce biomass, and if you burn this biomass and inject the CO2 not back into the atmosphere but in the geological underground, then you have created a net negative emission, and this may be in fact very useful in the future. So this is something you can accomplish only with CCS at the moment. And this means also we have to be careful if we want to keep this option open, that there is still enough storage capacity left in the second half of the century in order to be used for such a scheme, the combination of biomass with CCS. There are also some peculiar aspects of the importance of CCS with respect to, on the one hand, the climate target. I mentioned it in the summary in the beginning, and also of the issue of CO2 leakage. This is one of the risks that come with CCS. There are several risks, and my colleagues will talk about them, but the leakage of CO2 is one of them and has been analyzed in some detail in the past, also from economists. And so the first message is here that overall we would sequester in an economically optimal way roughly 1,000 gigatons of CO2. But only if the geological formation is sufficiently dense, if it's secure. So it means the mean residence time of the CO2 should be at least 10,000 years. A second number would be, if we go for this very strict target, in fact we need necessarily the negative emissions. And third, if the residence time was shorter, because there is on average some leakage in a larger way than we expected, then in fact the costs of these very strict mitigation targets become very large, because the option CCS would not work properly. It works so half and half, if you like. Yeah. So there is, in that sense, a necessity to clarify to what extent this can be confirmed that we have a long residence time of the CO2 in the underground. And finally, would like to highlight now a scheme by which companies that would, in an imagined market phase of CCS, perform CCS on a large scale. So only if it's done on a large scale it really matters for the climate. And the idea is as follows. A company may not be so worried about leakage that happens in the future. You may say, okay, we have a scheme right now under discussion where they have to buy additional emission certificates if we measure some leakage. But the question is this incentive enough for them to do a proper job today, to choose to chase for the most secure formations? And the idea of the scheme is now the following, that they have to buy a bond if they sequester CO2 today, and if they can prove that in 20 years, if they can prove in 20 or 30 years or so that the CO2 is still there, they have to prove it's still there. It's not an environmental authority that has to prove anything. It's a burden of proof is reversed, and they have to prove it. Then they get the bond back with high interest. And you may say, okay, this is some incentive for them to do a proper job, an additional incentive, but still the carrot, if you like, is in the future. It's not today. So here the additional idea comes in. If they can convince the capital market that they are running a proper, secure formation, if they give access to the data of measuring the CO2 and so on and so forth, then there might be other actors that are willing to buy an option on that bond right now. So if there are actors that are working on a long and investing on a longer time scale, like pension funds, then in fact there is a case for them to make business today if they do a proper and transparent job. And the idea would be to enhance transparency of this technology that comes with some residual risk, and by that also enhance the acceptance in the population. Thanks a lot.
Yeah, I would like to go on to give you a short outline about CO2 storage. And I would like to show both. So what you see here from this title already, this is all involved within this technology. So we have a lot of chances with the CO2 storage. So if there are the capacities we would need, Hermann just mentioned these capacities. I will say something about these capacities. There are risks involved, as with all technologies, especially technologies we are working on underground. And we have to take these risks into account. However, from all our experiences we do have so far, from natural gas storage, from the natural CO2 reservoirs we do have, as well as from the pilot sites and the demonstration projects, we can state here that this technology is feasible. So if you talk about capacities, you need to take this resource pyramid into account. This one outlines here the availability of CO2 storage, and what you can see is that the closer you have a look into the underground, the more certain you are with the storage capacity you do have. However, if you want to acquire as much as possible of the capacity of the underground, it gets more expensive. However, the theoretical capacity, these are the physical limits we do have. So what's the volume of the pore space in the underground? How much CO2 can we actually physically store? And then you need to go to the effective capacity. Here you do have some technical limits, some engineering limits, some geological limits that you have less storage capacity compared to the theoretical one. And if you go further up, you have to take into account legal and technical and the regulatory framework and infrastructure you can set up or you can't. And finally, here at the top of the pyramid, you do have the detailed matched capacity where you also have to take into account the distance between sources and sinks, for example. So what are the capacities worldwide actually? So you can see here this map, which is published by Michael et al. Last year. And here you can see that worldwide we do have a lot of capacities on the different continents. And this sums up to roughly 11,000 gigatons. And you just remembered, Hermann Held said we would need 1,000 gigatons. So this is 10 times what we would need to do something significant here. However, question here is still, is this the effective capacity or is it the practical capacity, if you remember just the pyramid I have shown? So this is a number which is as well published in the IPCC report from 2005. This is, let's say, the upper bound we do have available. So the lower bound is mentioned within this report with 2,000 gigaton, which is still enough to do something for the environment. So this is the chance actually of having CO2 storage as one part of our large portfolio we have to apply to do something to reduce our CO2 emissions. So, but there's no chance without risks. You can see here on this slide the risks we do have and which need to be assessed for every CO2 storage site in advance. And these risks need to be small enough that you do get the permission for the CO2 injection, that you really can say there is no danger for environment or humans. So what you can see here on this figure is you are injecting CO2 into the underground. You have a so-called multi-barrier system. You always have a cap rock above your system or above your reservoir, you can see here. However, there are a couple of potential leakage pathways you do have. So these are your wells, for example. These can be abandoned wells. These can be active wells. You do have here geological fault zones, which might be permeable or might be impermeable, and the cap rock could be discontinuous if you get further away from your injection site. And these leakage pathways, they are relevant not only for the CO2 but as well for the salt water. When we bring in here CO2, we are displacing a large volume of salt water which is moving away from the storage site horizontally if the cap rock keeps the salt water as well in the underground here. But if the salt water had the possibility to get through the cap rock and through the other cap rocks of our multi-barrier system, then finally it could happen that we contaminate with highly saline water our groundwater, our drinking water, and this needs to be surely avoided. However, what we know is that if you explore a site specifically, you do have the possibility, we do have the technology to store the CO2 for long term. However, you always have to take these risks into account. But this is actually the conclusion I've shown you already. So we do face here a feasible technology. And why is it feasible? To say it again. So we have these pilot sites like Ketzin, which the German Research Center for Geosciences is running close to Potsdam. This pilot site shows that CO2 storage is working on the research scale. And then we do have, as one example here, this is the map of Germany, we have these natural gas storage sites where we store the gas to balance the seasonal variance in gas usage. And in Germany we have more than 40 locations where CO2 is stored in exactly, not only, but in parts of the storage sites are exactly the same as the formations we are targeting for the CO2 storage. So here's experience from the technological side that we are able to inject large amounts, large volumes of gas into the underground. And finally, that it's long-term and safe, or can be long-term and safe, we learn from nature. There are CO2 reservoirs which contain almost 100% of CO2. So nature showed us how these structures look like, where you can store CO2 for millions of years.
I would take over with a little bit of a story about how the geothermal growth will be, geothermal energy. There will be a session on geothermal energy tomorrow. And I would particularly like to focus here on the interactions of this huge geothermal growth with CCS. To give you a summary, we think there are two major timelines in geothermal energy development. One is for 2020 and the other one is on longer term for 2050. These timelines are chosen because in policy making they are important, for example, for the renewable action plans, which has been published last year for 2020 and for 2050 on the IPCC and the IEA roadmaps. To start with 2020, if you look to geothermal, there are three major categories, which is to produce power from volcanic areas, that's one. To produce direct heat, for example, for the heating of greenhouses or spatial heating from geothermal aquifers. Those are the ones which correspond with CCS storage sites. And seasonal storage of heat and cold, and it's relatively shallow. For longer timelines, which will require a lot of fundamental research, we're looking to enhance geothermal systems. Those are at depth levels which are not which are deeper than geothermal aquifers and will not compete as well with CCS. What is important to say is that these geothermal energy use will grow very rapidly to 5 to 10% of our renewable energy portfolio. The major reason for this growth is purely economic. If you compare the different prices for renewable energy, what's often is done up till now is that it only compares the prices for the production of the energy and not the additional price you have to pay in the future, for example, to in your emission trading scheme for the CO2 emission, like for the fossil fuel, and for wind and solar, which have a high volatility in the production of the electricity on a daily basis, that you need storage costs. And geothermal does not need them. First of all, it's emission free. Second of all, it is a very good baseload energy. And even for power, but also for direct heat, we are at price levels which are almost competitive to fossil fuel, and especially to other renewable energies. So we think, given the changes which will happen for the emission trading scheme, but also in terms of putting a higher priority on renewable heat, which is really necessary, that geothermal will grow very rapidly. To give just a brief picture of the different geothermal applications, this is power from volcanic steam. Everybody knows geysers, of course. This is from Iceland. And volcanics relate to plate tectonics. So they are not everywhere on the world. They are on very specific locations. So you have a limited growth with power from volcanic areas. It will grow by a factor of 15 to the 2050 timeline, but it's limited. If we look to other geothermal sources than volcanic steam, there are two. That's the geothermal production from aquifers, which are almost everywhere on the world, as Michael Kuhn has shown in his previous slides. And the other one is enhanced geothermal systems, which I will not cover today. But for geothermal aquifers, basically what you do, you construct two wells, and the red well in this picture produces the hot water from the water-bearing layer at depth, which is typically at 1,000 meters depth or more. And it produces the water. Then at the surface, through a heat exchanger, the heat is extracted and used for heating of spatial heating and greenhouses, and then re-injected to the subsurface. The nice thing about these production systems, compared, for example, to CCS, is that you don't affect strongly the pressure balance in the subsurface because you don't really extract material. And the other thing is that there is no danger of, because you put the same material back, there's no danger of leakage because it's the material which was already there. One of major aspect of geothermal growth of this production from aquifers is that they are in the same layers where you find oil and gas. And in countries like the Netherlands, where you have an excellent, very high density of data collected the last 30 years and a lot of money invested to get those data, and if you have laws in place, like in the Netherlands, that all this data is publicly accessible, then it's very easy for investors in geothermal energy to have a good grip on subsurface conditions. And that's what we see reflected in the Netherlands, where there's over 80 geothermal exploration licenses, and in the last few years we have about 5 projects developed. And we see it as an important task to bring this data across in public information systems. And this is an example from a public information system in the Netherlands, which shows you the aquifer structures in depth. You can display interactive sections which show you the aquifers, and you can also immediately assess the properties and see how feasible particular locations are for geothermal energy. What is important to note is that the subsurface is marked by considerable uncertainties, and that's very, very dissimilar from other renewable energy, that you have a lot of variability in the subsurface, which you have to prove with a well to find out if it's really suitable. Well, to end with this synergy or competition with CO2 storage, there's not so much. We investigated the different properties which are required from the subsurface to either geothermal or CO2 storage. And although there are some properties which are similar, the most important differences are regarding the safety of the overlying rock, which should not permit any leakage with CO2, and those are indicated in green here in this diagram. This actually makes it more favorable in almost all aquifers in the Netherlands to produce geothermal. And actually it has been decided by our government that onshore storage of CCS will not happen in the near future onshore because of these safety issues. Thank you.
One may also raise the question, is it really a competition between two technologies, or do we have the chance to combine the two technologies? So I will give a brief statement on how to combine the two technologies. Many companies say it's not a problem to have CCS and geothermal at the same time. So why not using the billions which are spent for CCS from the European government and only the few tens of millions for geothermal and combine the two efforts, because we are both on a way on our learning curves. Efficiency in drilling technologies, in reservoir management, is a task for both technologies. And I think that there are also some good possibilities to bring together geothermal and CCS to enhance the storage volume, the potential, the storage potential for CCS sites. A rough estimate is for the next generation of CCS storage sites, you will be in the multi-million cubic meter area. If you want to use geothermal to enhance the volume, you will end up with something like 400 megawatt geoelectrically. And the third point I want to address is, as Hermann already mentioned, we should use the storage potential, which is, as all georesources, besides geothermal, endless. Not endless. We need to use it very wise. Because if we have 1 or 5 generations of power plants, the storage capability, we have to use it within the time we have to transfer our energy market to a real renewable one. And I want to address the next point from different sides. We discuss at the moment the tsunami in Japan, but the tsunami in Europe might be more global warming. It may be not a big wave of water flooding in, but it will have big migration effects because billions of people have to move, probably. So this is the biggest geoscientific experiment on Earth, what you see here. We pump as much CO2 into the atmosphere to look how our climate will change. Because geomaterials and the behavior is complex coupled, it's not always predictable. But we know that landslides happen, and we know that every activity in the underground has some risks involved. And from a resource point of view, if we make our business as usual scenario, and if we really try to go the way many scenarios show, we would need 5 to 6 blue planets. But I'm pretty sure that we only have one. So we have to be careful what we do and how we deal with our future. Thank you for your attention.
Okay, I see we have about 15 minutes left to ask some questions to these guys. Does anyone have a question?
Holger Croker, I'm a bit bewildered. I heard from Michael Kuhn that this technology is feasible. I heard from Mr. van Wees that the Dutch government says no way. And I heard from Mr. Held that we have to start with it at once. So how does it fit all together?
Yeah. Maybe I should comment that the decision of the Dutch government was based on the safety perception of the public, and there's the essential ingredient to this safety discussion, because the public perception is a reality, and with new technology you need first 30 years of practice to convince the public that it's completely safe. We are accepting safety when it's not yet proven when we travel to the moon. But for an energy transition, there are hurdles, and I think that's a particular ingredient for the energy transition discussion.
Yeah, so from what I have shown here very shortly, so you could have, you could go to the CO2 sessions, 2 days of CO2 sessions we do have. I'm pretty sure that it is a feasible technology. However, the discussion at the moment, which finally needs to get to a political decision, is not content-based. So it's we are not talking about our geoscientific knowledge here. Is it feasible? Is it safe? Or is it long-term or not? These discussions in the media, they are completely different. And here I can just agree or emphasize what Jan just said. So it's public perception is not necessarily the same as our geoscientific knowledge.
My statement was on the issue that if we do not start mitigating right now, things become much more complicated. So the economic numbers become more difficult, and the need for CCS may increase. This is what I try to emphasize. I was not saying that we need CCS right now. This is a different thing. If we start with the whole portfolio of mitigation options, then in fact the role of CCS is more modest. Whereas if we wait for very long, then we need negative emissions in the future, and without CCS there are no negative emissions possible at the moment. Nevertheless, what I would like to add is that I would, from an economic point, find it very important, in fact I didn't mention it, to have some demonstration plans on CCS right now, in fact, so that rather soon society knows to what extent they can rely on it on that large scale. This I would find very helpful, that in the best case society in 2020 or 2025 can take decisions how much money to put into which mitigation technology. So to have a build-up of renewable sources on a large scale, our calculations show that you need roughly 0.5 to 1% globally of GDP every year if you go into the economic optimum. And this is not what we are investing right now into the renewable sources. And in addition to that, it would be useful to have demonstration plans on CCS to learn about how to handle this technology. The fact that nature shows there are safe formations, this is one hand, but to find out to what extent a particular site would be similar to to this very great examples we see in nature or not. This is under development to my understanding at the moment. This is what geoscience tries to find out.
I guess there was, if I understand the Dutch situation correct, they say we want to store CO2, but maybe not onshore, but offshore. So we have different options to store CO2. The one is beneath the sea or beneath countryside. And they say first test it offshore. And I think that's also a good way to go, to say, if scientists, if from a geotechnological perspective it's feasible, we can do it. We should do it careful, we should learn to improve, to do even better. This can be done also very well offshore, and they have in Dutch very big gas producing areas where the space is there, where you could fill this area. So they have very good reasons to go offshore as well, because there are the really big sites as well.
Any other questions? Yes.
Liz Gallagher, Environmental Research Web. I have a question for Dr. Schilling about how you propose combining the two technologies, CCS and geothermal.
I think that one possibility would simply be that a company shows that it's possible to use the space for both technologies, simply to prove it. The other idea is, if you use geothermal, there is a lot of heat released out of the hot water before you pump it back. And if you have water or other fluids and cool them down, they get a higher density. This means the volume became lower. So if you pump cold water into the underground, you get to the primary pressure a negative pressure. As Michael has discussed, we need the pore space which is filled with water. You can squeeze it out to the side, or if you cool the sides, you could generate additional pore space simply by geothermal. And then geothermal may become more effective because you would have a double benefit. But that's an economical task then. At the moment, this is simply an idea, one of the ideas possible. It does not mean that it will work. It does not mean that it's the best way to deal with reservoir management. But at least one should think of combining technologies, and this would be one possibility how to combine and have an additional effect. Another possibility is, if you remember the slide from Michael about the multi-barrier system, you could even pump out the hot water from the reservoir where you want to store CO2 and pump the cold water or part of the cold water in the reservoir above the CO2 layer. So you could generate a negative pressure gradient, which would enhance the security that even if a drill site would be open, there would be no flux of CO2 out of the reservoir. So you could generate ideas if you accept not to make a competition which may be more political than real technological, and think how can we combine and what surplus can be generated by combining the method. I would say you could generate more pore space, you could use a lot of heat out of it, and the wells would be paid simply by another technology, and you could enhance the security because you would have half the pressure at the end on the cap rock, effective pressure, which would double the security or double the pore space to be used.
No more questions? Okay, then I think I'll wrap this up. And I'd like to be the end of this press conference. Well, thank you all for your attention.